Hi everyone, it's me, Mr. Wilson again, with another one of my videos where I teach you how I hope you're all excited for this week's YouTube giveaway where I'll be giving away the notes for this week to everyone who watches this video, because that's literally what this video is. It's the Week 7 recap coming at you like a spider monkey. The first topic up today is midsegments of triangles. To illustrate this, we're going to draw a triangle and label it ABC. A midsegment of a triangle is a segment that connects the midpoints of two sides of a triangle. So here, the midpoints are X, Y, and Z. If I connect any two of them, say X and Y, I get a midsegment. Every triangle has three of these. So I could draw XY, XZ, or ZY. Our midsegment theorem says that the segment connecting the midpoints of two sides of a triangle is parallel to the third side and is half as long. So in this diagram, ZY is parallel to BC, and you could either say ZY equals 1/2 of BC or BC equals 2 times ZY. Additionally, since X is the midpoint of BC, BX and XC are also 1/2 the length of BC, which implies that the segments ZY, BX, and XC are all congruent. I have one more property to introduce, but first we need to talk about scale factors. The scale factor is the ratio of the lengths of two corresponding sides of similar polygons. In this diagram, triangle ABC is similar to triangle DEF with a scale factor of 2 to 1. That means that the ratio of corresponding sides is 2 to 1. Notice that across the tops of the fractions, all of the values come from the same triangle, and across the bottom, all of the values come from the other triangle. Also notice that corresponding sides are always in the same fraction. AB over DE, BC over EF, and AC over DF. I can replace those symbols with the values of the side lengths, and you should be able to see that these are all fractions that reduce to 2 over 1. One more thing that I want you to notice is the order in which we wrote the scale factor. It matches the order in which we wrote the similarity statement. So if I had written DEF is similar to ABC, I would have to change the scale factor to 1 to 2. So let's apply this to midsegments. A midsegment divides the triangle proportionally, and it gives us two similar triangles. In our example, triangle AZY is similar to triangle ABC with a scale factor of 1 to 2. And in case it's not clear what I'm talking about, here's triangle AZY. I'm honestly frighteningly good at PowerPoint. This leads perfectly into the triangle proportionality theorem. It says that if a line parallel to one side of a triangle intersects the other two sides, then it divides those two sides proportionally. I realize that's a lot of words, but here's what that looks like in the diagram. BC, one of the sides of the triangle, is parallel to ZY, which intersects the other two sides. That means that the ratio of AZ to ZB is equal to the ratio of AY to YC. Since we have two equal ratios, we have a proportion. Now in this diagram, ZY happens to be a midsegment. However, I could move ZY down here and the proportion would still be true. And I could move it up here and the proportion would still be true. So it doesn't have to be a midsegment, it just has to be parallel to one side and it has to pass through the other two sides. Now for the next theorem, we need to recap something from Unit 3 when we talked about reasoning and logic. Conditional statements have a hypothesis and conclusion, which we write symbolically as P and Q. The conditional statement takes the form if P, then Q. The reason we're reviewing this right now is because we're about to use the converse of the triangle proportionality theorem. If you don't remember, the converse takes the form if Q, then P. So we're about to simply switch our hypothesis and conclusion. So coming back to the theorem, the converse of the theorem states that if a line divides two sides of a triangle proportionally, then it is parallel to the third side. Because this theorem and its converse are true, I can replace this right arrow with a double arrow to show that it goes both ways. We have two more theorems to cover, and neither of them really have names. The first one involves parallel lines cut by transversals, which might remind you of Unit 2. If three parallel lines intersect two transversals, then they divide the transversals proportionally. One such proportion would be UW over WY equals VX over XZ. Notice that UW and VX are both cut by lines R and S, and WY and XZ are both cut by lines S and T. UW and WY are both parts of line P, and VX and XZ are both parts of line Q. The parallel lines are also divided proportionally. So for instance, YZ over UV equals OZ over OV. Pause the video if needed and see if you could figure out how these four segments relate to each other. As a hint, we're talking about this because of similar triangles. And in this diagram, triangle OYZ is similar to triangle OUV. Our final theorem says that if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. In this diagram, that means AD over DC equals AB over BC. AD and AB are on the same side of the ray, and DC and BC are on the other side of the ray. AD over DC is the ratio of the two segments cut by the ray, and AB over BC is the ratio of the two sides not cut by the ray. So that's week 7 for you. If this video helped you, make sure you smash that like button and subscribe for more cringy math content. As always, I want to end this video by thanking my supporters on Patreon, whose names should appear on the screen now.